Alright, in this section, we're going to talk about something called relations. And the reason we're going to talk about relations is we want to build towards a special type of relation called an equivalence relation. Also, relations are going to be important to us when we talk about things called functions a little bit later as well. But our goal right now is to work towards these things called equivalence relations. And why are they important? They're important because in a lot of infinite sets, various groups of objects, quote-unquote, behave the same way as each other in the context that we're interested in. So, if these objects that all behave the same follow some equivalence relation, we can use that very powerful idea to be able to study these infinite set of objects, but just by picking one representative and studying that object from these things that we'll call equivalence classes. So in some sense, these equivalence relations allow us to take an infinite number of things and make it into one thing, or at least allow us to study one thing. So it takes infinite to finite, which is always great in mathematics. So, first thing we have to talk about is a relation. What is a relation? Well, we have two sets. Let's call the relation R. And we have two sets. Let's call them A to B. And we say a relation from A to B. And the order is important. We're going to call the set on the left, in some sense, we're going to call this the domain. And we're going to call this set the codomain. And I'm being a little bit sloppy. It's not actually the domain. Once we talk about functions, it'll be the domain. But we're thinking of it something like our initial set, and B is our final set, in some sense. And so what is it? Well, in the simplest terms, all it is, it's a subset of the direct product of A and B. So it's just some of the elements of this direct product. And to say that one of the elements of our direct product, one of our ordered pairs, is in the relation, we say that A is related to B, and we usually use this notation, A, R, B. So R in this case is the name of our relation. If we had a different name for our relation, we'd use a different letter there. Name of relation. I mean, you can think of these, of course, just as subsets of the direct product of two sets, or the Cartesian product. But most times we think about them, they're going to satisfy some rule. So that's going to be our underlying idea, is that an element from set A is related to an element from set B if there's some rule that gets satisfied. So that's how we're thinking of them. Let's do a little example, just to make sure we understand what's going on here. Okay, so A in this case is going to be the set 1, 4, 9. B is going to be the set 2, 5, 6, 10. So our relation, R, is saying that A is related to B via this relation R exactly when the sum of A and B is prime. So that's what we want to determine. So let's see if we can define the set R first. And maybe as an exercise, I think it's a good idea to work out A cross B. See if you can write down all of the elements of A cross B as a little exercise. If you forget, just watch the appropriate videos. I think they're back when we were talking about sets. And remind yourself how this Cartesian product or direct product works. So I'd like you to calculate this Cartesian product or direct product, and then calculate the subset of this that is indeed the relation. So it's elements where if you add the two bits of your ordered pair together, you get a prime number. So pause the video now and give that a go. Okay, I'm going to magically write down the set of all ordered pairs in A cross B here. And here they are right now. So we have, remember, it's each element from A in the first place paired with each element from B in the second place. Every possible combination of one element from A and one element from B. Here they are. So now we just have to check which of these satisfy the rule. So we'll just add together the components and see if they satisfy our rule. 1 plus 2 is 3. We do indeed want to include this guy. 1 plus 5 is 6. We're not going to include 1, 5. 1 plus 6 is 7. 7 is prime. We'll include 1, 6. 1, 10. 1 plus 10 is 11. We're going to include that. We can just check each element like this. 4, 2, we don't include. That sum is 6. 4, 5, we don't include. That sum is 9. We don't include 4, 6 or 4, 10, since those sums are not prime. And 9 plus 2 is 11. We include that. 9 plus 5 is 14, not prime. 9 plus 6 is 15, not prime. But 9 plus 10 is 19. That is prime. So R is the subset of A cross B of 1, 2, 1, 6, 1, 10, 9, 2, and 9, 10. So there's R, that's our relation R. And we know, of course, R, you can check, is a subset of A cross B. And of course it is. We made it from elements of A cross B, so it's obviously a subset. So the next question that we have to answer here is 1 related to 10? So remember, this is asking, this is just rewording, is the element 110? Is that actually in R? Is that an element of R? And of course it is. Here it is here. The element from A is 1. The element from B is 10. 1 is related to 10. So we're good to go. Is 4 related to 5? 4 is not related to 5. First of all, since 4 plus 5 is 9, 9 isn't prime. So the answer to this question, the first one, is 1 related to 10, is yes. And is 4 related to 5? No. And of course, just a reminder that relations will change depending on what rule you give them, of course. I could come up with a different rule for A and B here. Maybe I want A minus B as prime. Or it could be even something like, well, if you look at the English word representing each number, we could say something along the lines of, or we could define a relation that an element in A is related to an element in B exactly when the English words have the same number of letters, or whatever you want. You can come up with any rule you want. There's nothing except your imagination stopping you from creating a rule. So that's how it works. And I just want to show you another way of thinking about relations as well, and sometimes this is helpful. You can do it in some sort of, it's called a digraph, I guess. So you can draw all of your quote-unquote domain set in one bit and all of your codomain set in the other bit. So we have 1, 4, and 9, and here we have 2, 5, 6, and 10. And then if two elements are related, we'll put an arrow between them. So we'll call the relation R be these arrows. So 1 is related to 2, so I'll put an arrow here. 1 is related to 6, 1 is related to 10. Okay, 4 is related to nothing. You can see here 4 isn't related to any of the elements in B. That's fine, that's allowed. And 9 is related to 2 and 10. So I'll draw an arrow to 2, and I'll draw an arrow to 10. So you can see here, sometimes you have elements in your domain set that are related to more than one thing, 2 things, 3 things, whatever. Sometimes they're related to none. And in your codomain set, sometimes they're related to 1, 2, none, whatever. So any possibility is totally good just to call it a relation. There are special types of relations, especially these things called functions, where we want everything in our domain set to be related to exactly one thing in our codomain. And in that case, we do care about how many things are related to each element, at least in our domain. But if you're just an arbitrary relation, it doesn't really matter. So this is another way of thinking about this relation R. So you can write it either as a subset of the direct product, or you can write it in terms of this digraph here. It conveys the same information, though if you're asked for the set, if you will, you'll have to give the set of R, of course. So I want to talk about a couple definitions here, and we're going to be a little more precise with what I mean by domain. This is why I put the previous domain in quotation marks. But the domain, well, let's see what it says here. Let's read the mathematical notation together. So the domain of a relation R is the set, and we give it the name dom of R. And it's the set here. And I think it's a good exercise. Pause the video and see if you can parse what this definition is saying, what elements are in this set. And do the same thing for the range. And there's a little typo here. This should be R-A-N for range, not D-O-M, of course. So pause the video now and see if you can determine what these sets are, dom of R and ran of R, and what they represent. Okay, well, let's read this. It's all elements of A such that there is an ordered pair that has A as a member. So that's what this is saying. And for the range, it's kind of the opposite thing. So rather than the first element, so in A, it's the second element, so in B. So let's look at dom and ran of R in the previous example. So dom of R, so it's going to be a set. And remember, the elements of dom of R are elements of A. They're not ordered pairs. They're elements of A. So it's the elements of A that are related to something. And they are, in this case, 1 and 9. So they're all the elements that are related to something. 4 isn't related to anything in B, so we're not going to include 4 in our dom set. And our ran set is all elements of B that are related to something. And they are 2, 6, and 10. So that's the range of this relation. And of course you can see, remember, these guys are subsets of A and B respectively. Because in their definition, they're made up of elements of A for dom and elements of B for ran, but with some extra condition. So obviously they're going to be subsets of where the elements are coming from. The next thing I want to talk about is a relation on a set. So when I say a relation is a relation on a certain set, say A, What I mean is that if the relation is called R, it means R is a subset of A cross itself, A cross A. So I'm thinking of my Cartesian product as just being the set with itself. And sometimes you might see A cross A. Some people instead might write A cross A as A squared. And they kind of think about this Cartesian product like set multiplication in some sense. So they'll write A squared to mean A cross A. So you might see that. Let's take a look at an example of a relation on a set. Okay, so let's look at this example here. I have a relation. I called it R again. Again, there's nothing special about the letter R. You could use whatever letter you like to talk about a relation. And it's going to be a relation on a set A. So that means that R is a subset of the Cartesian product A cross A. And A, in this case, are the elements A, B, C, and D. So here is the relation given as a digraph. So let's kind of make sure we understand what this is saying. So anytime there's an arrow going from one element to another, it means that the element at the start of the arrow is related to the element at the end of the arrow. So this arrow here, this says that A is related to itself. A is related to A, since there's an arrow starting at A, going to A. This arrow says that A is related to B, so A, R, B. And here we have these two arrows. Let's look at this BD. So it's a double-sided arrow. And I'm trying to indicate here that the relation goes in both ways. So B is related to D, and D is related to B. So this is kind of two arrows in one. An arrow going this way, so starting at B, ending at D, and an arrow starting at D, ending at B. So what I want you to do is I want you to write R in set notation. Write all ordered pairs that are in the relation R. So pause the video now and try that yourself. Okay, now that you're back, let's go ahead and do this. So here we have A is related to A, so I know that I have the element AA. And I'm going to just check that off just to make sure that we get all of our arrows in our set. I'm just going to check off the ones that we get. This arrow is A related to B, so we have A, B. Let's do all the ones that start with A first. A isn't related to C. And just to be clear, if there's no arrow, if the two elements aren't related, you'd write it like this. A is not related to C. See, of course, you just put a line through the relation symbol like that. That's our most common symbol in mathematics, is putting a slash through something and say it's not that. So AC isn't in R, so we're not going to include it. But AD is. We have an arrow starting at A, going to D, so AD is in R. A is related to D. Let's look at B. B is related to itself, but it's not related to A, of course. There's no arrow starting at B and going to A. B is not related to A, even though A is related to B. That's fine. You can have relations that don't have that. We call it a symmetric property. We'll talk about that in a little bit. But B is related to itself, so we have B, B, that's this guy. We have B is related to C. That's that guy. And we have B is related to D. That is this guy. Okay. Now let's look at C. Well, C has no arrows going out from it, so C isn't related to any element with C as the leftmost element. So nothing starts with C. So let's look at everything that starts with D. We have two arrows. We have D going to A, so D is related to A. And we have D is related to B. Okay, so this is our set R here. This is our relation. Again, there's no real rule that I came up with. I just wrote down the relation as a digraph, and here are all the ordered pairs that are elements of our relation R. So in the next video, we're going to talk about properties of relations. And that's kind of the reason that we're studying relations. We want nicely behaved relations. And so the properties we're going to care about are things called reflexive. Reflexive means it does it to itself. So reflexive means an element is related to itself. Symmetric means that if one element is related to another, the reverse relation also holds. So this is kind of a sub-example of the idea of being symmetric. This is a sub-example of the idea of being reflexive. And the other one that we care about is something called transitive. And it basically says that if there is a path of relations going from one element to another, so if A is related to B and B is related to D, if you have this path of two things, you can get there directly. A is related to D. So you get these triangles. And that's what transitivity is, but we're going to be a lot more formal about that in the next video.